Video, I will be talking about prime numbers applied in number theory, mainly how it is applied in multiplicative functions. Okay, so just an introduction. What is a prime number? I'm sure a lot of you know what it is. It's just a positive integer that has exactly two factors, namely the number itself and 1, and they are distinct. So for example, you have number 2, right? Because the factors of 2 are 1 and 2, and let's say the number of 11, right? The number 11, the factors of 11 are 1 and 11. The number 6 is not a prime number because you have 1, 2, 3, 6, right? This is more than 2 factors. And the number 1 is not a prime number because, well, the only factors of 1 is 1. So therefore, it's not a prime number. Okay, so 2, 11, 5, they are examples of prime numbers. So here are some appetizers. Let's start with some common theorems that uses prime numbers, namely the fundamental theorem of arithmetic, which is also known as the prime factorization and decomposition theorem. And what this is it states that every natural number greater than 1 can be represented uniquely as a product of primes up to the order of factors. And we will use this fundamental theorem of arithmetic later on in the video. So some examples. For example, the number 1200, I can write this as 2 to the power of 4 times 3 to the power of 1 times 5 to the power of 2. But I can also rewrite this as 2 squared times 5 times 3 times 5 times 2 squared. Okay. Another theorem that uses prime numbers is that there are actually infinitely amount of primes. And Euclid proved this using proof by contradiction, and it is known as Euclid's theorem. Okay. You also have the Fermat's Little theorem, which is a basis for Fermat's primality test, which is a probabilistic test to determine whether a number is a probable prime. So in essence, Fermat's Little theorem helps to find remainder quicker when dividing from large dividends, and it uses congruences. Okay. And there's also unproven statements, conjectures regarding prime numbers. For example, Goldbach's conjecture. So is it true that every single even number greater than 2 can be written as a sum of 2 primes, right? We have calculated large numbers up to large even numbers that are indeed sum of 2 primes. But there's no way to prove that this is true for infinitely amount of even numbers greater than 2. All of them, I should say. So far, we have not found that out yet. There's also the twin prime conjecture, which states that there are an infinitely amount of primes p such that p plus 2 is also prime. So we do know that there are infinitely amount of primes, but is it true that there are infinitely amount of primes such that, 2 plus that, which is also an odd number, is that also prime? Okay, so we don't know. Yeah. So prime numbers, they have to be odd except for the number 2, but besides that, the number 2, every other prime number is odd. So that's the twin prime conjecture. Okay, let's get into the crux of the matter, the entree of this video. Okay, so it's mostly going to be focused on multiplicative functions. And this is probably a topic that will be studied in the number theory class. So let's consider an arithmetic function. And an arithmetic function, or an arithmetic function, is simply just a function f that maps positive integers to the complex numbers. N maps to f of n. Now, usually when we study arithmetic functions, the codomain, the target, is also possibly going to be positive integers too, but it doesn't have to be in positive integers. A lot of times it will be, but the most important part is that the domain needs to be positive integers. Okay, so multiplicative functions are arithmetic functions such that, right, f of 1 is equal to 1, and f of a times b is equal to f of a times f of b, right, if GCD of a and b is equal to 1. So if a and b are co-prime, then the function of the product is just the product of their functions. Or I should say, the f evaluated at the products is the same thing as the products of f evaluated at each of these two co-prime numbers. Okay. And we have something called completely multiplicative as well. So a completely multiplicative function basically ignores this latter statement here. So a completely multiplicative function is an arithmetic function where f of a times b is equal to f of a times f of b, regardless of them being co-prime or not. Okay, so it works for all a and b in Z plus. However, here for multiplicative functions, they have to be co-prime. Now, if a function is completely multiplicative, it implies it is multiplicative, right? So if it works for every single integer, it works for integers that are co-prime. So why is this helpful? Multiplicative functions helps break down large problems into smaller, manageable pieces. And we do that by prime factorizing a number. So, for example, if you want to compute f of n, where n is a positive integer, this is the same thing as f of, let's say, p1, a1, all the way to pr, ar. So this is just multiplying. There might be some other primes in here. I don't know. But this is what I have for now. Now, since f is multiplicative, right, I can rewrite this as f of p1 to the power of a1 times f of pr ar, all the way up to f of pr ar. Each of these pi's, where I is between 1 and r, they're all co-prime to each other. So I cannot split this up, right, because p1 is not co-prime with itself, p1. And similarly here, pr is not co-prime with pr, but pr, p1, p2, they're all co-prime with each other. And even if you raise them with exponents, they're still co-prime with each other, so you can break it up like this. Now, the notation I will use, instead of using a1 and ar or a2, a3 as exponents, I'll use something called evaluation. So I'll explain that in a sec, but instead of writing n as like p1, a1 times ... times pr, ar, I'll write n as the product of all the primes that divide n of p to the power of the valuation of p of n. So what the heck is this symbol, right? The valuation of p of n is simply just the exponent that this prime p is raised to during the prime factorization of n. So, for example, if you have some number n is equal to 2 squared times 5 cubed times 11 to the power of 16, then what we have is that the valuation sub 2 of n is equal to 2, because the exponent is 2, the valuation sub 5 of n is equal to 3, and the valuation sub 11 of n is equal to 16. Okay, it's just the corresponding exponent. All right. So given this, then because f is multiplicative, then we have, this is the same thing as the product of all the primes that divide n of f of p to the valuation sub p of n. Okay. So in order for us to, of course, do this, we have to know the prime factorization of n first. Okay, so here are some examples of multiplicative functions. And actually, these two examples I'm going to give are actually completely multiplicative functions, but being completely multiplicative implies they are multiplicative. These are two easy ones. So you have the 1 tilde constant function that basically maps everything to 1. So 1 of n is equal to 1 for every n in positive integers. Okay, we're talking about multiplicative functions here, so our domain is only positive integers. Okay, this is multiplicative, or actually it's completely multiplicative. And the proof is not too hard, because if you have 1 of ab, this is just 1, right? Ab is just some other integer, is just 1. 1 is equal to 1 times 1, which is equal to 1 of a times 1 of b, or 1 tilde of a times 1 tilde of b. In some literature, they write the 1 function literally like this, like 1 of n, but sometimes I write my ones like this as well, so I put a tilde on top to represent it's the function, it's the 1 function. Okay. And the second example is the identity function, which I will denote as capital I. So I of n is equal to n for every n in the positive integers. Oh, I should finish this off with a box. And this is completely multiplicative. So it is completely multiplicative, which implies it is multiplicative. And similarly, the identity is also completely multiplicative, which implies it is multiplicative. So the proof is as follows. If you have I of AB, this is the same thing as AB because it's identity, but A is the same thing as I of A, and B is the same thing as I of B. Okay, so we are done. Cool. So I'm going to introduce something called the Dirichlet convolution, which will help us utilize multiplicative functions in a more applicable way. Okay. So the Dirichlet convolution is an operator that uses the star. It uses the star operator, which is the same star operator you see in the convolution in differential equation classes. Okay, so if you have two arithmetic functions, f and g, then their Dirichlet convolution, which I'll denote as f star g, right, is still that star. Okay, so the Dirichlet convolution of f and g, right? That's this new function over here. It's still multiplicative, by the way, but I'll define it right now. Of n is equal to all of this stuff. So the sum of all d dividing n of f of d times g of n over d, which is the sum running over all positive divisors of n. Okay, and I say positive divisors because f and g are arithmetic. Okay, so then their inputs can only be positive integers anyways. So we say d is positive divisors of n, not any negative divisors of n. So this is how it's defined, I should say. So this Dirichlet convolution, the star operator is associative, it is commutative, etc. Okay. So let's tackle some theorems. So the first theorem is that if you have two multiplicative functions, so if you have f and g are multiplicative, then what does this imply? This implies that their Dirichlet convolution f star g is also multiplicative. All right, so I will not prove this here, but if you consider two multiplicative functions using this definition, right, their Dirichlet convolution f star g is multiplicative. So definition, okay. Let f be arithmetic. Then we have f hat of n, which I'll define to be the sum from of all the positive divisors of n, or the sum running over all the positive divisors of n, of f of d. I guess from here you can conclude that f hat is also multiplicative. Oh, sorry, not multiplicative, arithmetic. Because the input n is an f hat, right? So n is a, I should state that n is a positive integer, okay? And f is arithmetic, so yeah, so based on this setup, f hat is also arithmetic. And one thing to also note, another thing to note is that this f hat is equal to f convolutioned with the one function. And the reason why is because, well, if you look from here, this definition, this is the same thing as d divides n, f of d. And then what am I multiplying by? I'm multiplying by g of, let's say, or I should say 1, right, times 1. But 1, I can write it as 1 tilde of n over d, okay? But 1 tilde of n over d is just 1, so f of d times 1 is still f of d. So yeah, we see here that f hat is just the Dirichlet convolution between f and 1 hat. And this leads to a second theorem, okay? And it states that if f is multiplicative, then what we have is that f hat is multiplicative. Multiplicative. Okay, I'll actually call this theorem 1 and theorem 2. The proof of this is not hard at all, because it basically just uses theorem 1 and the definition that I stated above. So since, I guess, f hat is equal to f star 1 hat, or 1 tilde, and f and 1 tilde are both multiplicative. So we know that 1 tilde is multiplicative already, and we also know that the premise, we also know that from the premise, the first antecedent, f is multiplicative as well. So f and 1 hat are both multiplicative. Then we have that f star 1 hat, which is 1 tilde, which equals to f hat, is multiplicative by theorem 1. Okay, so it's not too hard to prove. All right. So let's get on to some examples. So the first example is going to be the divisor function. Actually, I'll call this definition. So let tau be arithmetic. And when I say arithmetic, I mean let tau be an arithmetic function. Tau is known as the divisor function. So it basically counts the number of positive divisors a positive integer has. So let tau be arithmetic such that tau of n is, right, it's defined to be the cardinality of the set of positive integers d such that d divides n. Okay, now there's a lot of vertical pipes here, I'm sorry, but yeah, it's just I such that, right? Some people use colon. I just prefer to always use a pipe. Maybe this divides could be this pipe could be a little smaller. Cardinality maybe could be a little bigger here for the pipe. So how would we write this using, let's say, the Dirichlet convolution, right? Something regarding the sum running over all positive divisors of n. So we know that for each positive divisor of n, right, that counts as 1, right? If you have 2 divisors, you have 2. You have 3 divisors, you have 3. If n has 5 divisors, there's 5. So each divisor of n contributes to 1. And when it comes to counting how many divisors n has. So I'll just put 1 there. But 1 is the same thing as 1 tilde of d. All right. And what's nice about this is that from this definition, okay, right over here, our 1 tilde is our f, right? It's our arithmetic function. So this means that the sum of d dividing n, or running over all d dividing n of 1 tilde of d, this is just 1 tilde hat of n. But we see here that 1 tilde hat is equal to tau. And from theorem number 2, since we know that our f here, which is 1 tilde, is multiplicative, this means that 1 tilde hat is also multiplicative. And 1 tilde hat here is equal to tau. Okay, so we get that tau is multiplicative. All right, so that's a neat observation. So now let p be prime and a be some positive integer. Then let's try to figure out what tau of p to the power of a is. So it's going to equal to the cardinality of the set of positive integers that divide p to the power of a. Well, what are they? You have 1, right? 1, obviously 1, right? 1 divides into every single positive integer. So you start with 1. And you have p to the power of 1, dot, 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 all the way to p to the power of a. So how many is this? Well, I'm just going to say 1, dot, 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 right? Because a is a positive integer, so a could equal 1 here. But 1 is p to the power of 0, right? So if there are a primes here, and there's, or a numbers here, and one number here, then in total there are a plus 1. right? Because 1 is the same thing as p to the power of 0, right? So we have 0 all the way up to a, so that's a plus 1 of them. Okay. And what's useful about this is that if you have a positive integer n, right, then what we have is that tau of n is equal to tau of, so I'm going to use the product notation as well as valuations. The product of all primes dividing n, or running over all primes that divide n, of p to the power of valuation sub p of n. Since we know that tau is multiplicative, we can write this as the product running over all the primes that divide n of tau of p to the valuation sub p of n. All right. And why is this helpful? Because we know exactly what this is. Okay? If we simply just substitute this with a, right, the v sub p of n with a, then we just have the product running over all primes that divide n of valuation sub p of n plus 1. All right, and that's it. So this is how you can compute the number of positive divisors a positive integer has, right? It's the product running over all the primes that divide n of the valuation sub p of n plus 1. Here's a quick example. Let's say you want to find out how many divisors a billion has. So tau of a billion, which is tau of 10 to the power of 9. This is the same thing as tau of 2 to the power of 9 times 5 to the power of 9. So since 2 to the power of 9 and 5 to the power of 9 are co-prime, and you know that tau is multiplicative, this is the same thing as tau of 2 to the power of 9 times tau of 5 to the power of 9. Okay, so tau of 2 to the power of 9 is simply just the, if n here is 2 to the power of 9, well, the only primes that divide 2 to the power of 9 is 2, right? So we have 2, right, the valuation sub 2 of 2 to the power of 9, which is going to be 9 plus 1. And similarly here, if n is 5 to the power of 9, then all the primes that divide 5 to the power of 9 is just 5. So the valuation sub 5 of 5 to the power of 9 is just 9. And once again, we have 9 plus 1. So we have 10 here and 10 here. 10 times 10 is 100. Of course, the divisor function tau, if you know the prime factorization of a number, you don't need like multiplicative functions or number theory to solve this problem, right? To figure out the formula for tau. Because from combinatorics, using the fundamental counting principle, you know that, let's say for 1 billion, you have 2 to the power of 9 and 5 to the power of 9. Well, the exponent for 2 can range from 0 to 9, which is 10. And the exponent for 5 can also range from 0 to 9, which is 10. So for each exponent of 2 you choose between 0 and 9, you can choose 10 exponents for 5 that also goes from 0 to 9. So 10 times 10 is 100. But nonetheless, we can use multiplicative functions to figure out the formula for tau as well. Okay, so this tau is really useful because it appears in a number of remarkable identities, including relationships on the Riemann zeta function and the Einstein series of modular forms. These were also studied by Ramanujan, who gave a number of important congruences and identities. So that's the divisor function. Now let's move on to its big brother, the summatory function, sigma. Okay, so let sigma be arithmetic, and sigma here is it's the divisor summatory function. Okay, and what it is that sigma of n just sums up all of the divisors of n, okay, such that sigma of n, we define it to be, well, it runs through all the d's that divide n of d, right? Because if d is a divisor of n, it just sums all of the divisors up. Okay, well, d, how can we write d as a multiplicative function? Okay, so d is the same thing as I of d, right? So our f here is I, and because our f here is I, then this is just equal to I hat of n. But from here, I hat, we know is multiplicative because I is multiplicative. So I hat is multiplicative, and we know that I hat is equal to sigma. Okay, so therefore, what we conclude is that sigma is multiplicative, since I is multiplicative. Okay, now let's try to figure out what sigma of p to the a is. So let p be prime and a be a positive integer. Then this implies that sigma of p to the power of a is just equal to 1 plus p squared plus all the way to p to the power of a. Okay, and this is a geometric series, right? It's just the sum from k equals 0 of a, p to the power of k. This is 1 minus p to the power of a plus 1 over 1 minus p, if you know your geometric series formula. If you multiply top and bottom by -1, you also get that this is equal to p to the power of a plus 1 minus 1 over p minus 1. Okay, but I'm going to stick with this 1 minus p version instead. So now let n be a positive integer. This implies that sigma of n is equal to sigma of the product running over all primes dividing n, p to the valuation sub p of n. Sigma is multiplicative, therefore this is the same thing as the product running over all primes of dividing n of sigma of p to the vp of n. And this is equal to the product running over all primes of n. Well, sigma of p to the v sub p of n, just once again pretend you can just substitute this vpn with a, right? Then we have the product of what? All of this 1 minus p to the v sub p of n plus 1 over 1 minus p. Okay, and that's it. So earlier, I had 1 billion with tau, and 1 billion has 100 positive divisors. But what is their sum? Well, let's see what their sum is. Okay, so what is the sum of all the positive divisors of 1 billion? So let's say sigma of 10 to the power of 9. Sigma of 10 to the power of 9 is equal to sigma of 2 to the power of 9 times 5 to the power of 9. But because sigma is multiplicative, this is equal to sigma of 2 to the power of 9 times sigma of 5 to the power of 9. Okay. So now, for 2 to the power of 9, right? Sigma of 2 to the power of 9, well, what is that? Sigma of 2 to the power of 9 is just 1 minus this 2 to the power of 9 plus 1 over 1 minus 2. And then sigma 5 to the power of 9 is just 1 minus 5 to the power of 9 plus 1 over 1 minus 5. And this I computed to be 2497558,338, which is, what is this? 2,497,558,338. Okay. So this sigma is frequently occurs in the study of the asymptotic behavior of the Riemann zeta function. If you're interested, the various studies of the behavior of the divisor and summatory functions are sometimes called the divisor function problems. So all in all, multiplicative functions are very helpful, but the thing is we need the prime factorization of n first. If n is large, then is n prime? And if not, if it is composite, how do we prime factor it? So there is some time complexity involved in doing both, whether it is determining whether a number is prime or not, and if it's composite, how do you decompose it? And this is studied in computing science and higher level number theory, namely analytic number theory. The stuff that I've been going over so far in this video is more algebraic number theory. Okay, so a lot of just formulas and plug and chugging. Okay. Now I do want to end off with another multiplicative function for dessert, which is used a lot in the computing science field, which is the Euler totient function, and is also known as Euler's phi. Okay, and basically what it is that if you have a positive integer and you take phi of n, it just outputs the number of integers that are less than or equal to it that are also co-prime to it. So we know phi is multiplicative because phi is equal to the identity convolution with mu, and mu here is the Mobius function, which is multiplicative. I will not be going over what that is, but because we have the convolution between two multiplicative functions, phi is multiplicative. So let me just define what phi is. So suppose you have n that is a positive integer, then this implies that phi of n is equal to the cardinality of the set of integers m that are between m and n, such that m is co-prime with n, or GCD of m and n is equal to 1. Okay, and I put a equal here and not strictly less than, because n could be 1, right? If n is 1, then GCD of 1 and 1 is 1, therefore phi of 1, right? We can see that phi of 1 is equal to 1. Okay, so it's once again satisfied the property for multiplicative function that f of 1 is 1 if f is multiplicative. So this Euler's phi, the Euler totient function, is used in BCH codes, and it's also used in RSA encryption systems, which is widely used for secure data transmission. Okay. I do want to go over the formula on how to compute some values using Euler's phi. So if you have phi of p, well, the numbers that are co-prime with a prime p are all the numbers that are less than it, except for itself. So from 1 all the way up to p, that's p numbers, but p is not co-prime with p, but everything else less than p from 1 is co-prime with it, so it's just p minus 1, right? Let's say, you know, if p is 5, then how many numbers are co-prime with p that are positive integers? You have 1, 2, 3, 4, right? So 4 is the same thing as 5 minus 1. Okay. Then if you have, but more generally, right, if you have a being a positive integer, then what you have is that phi of p to the power of a is equal to, well, let's see how we would find out how many numbers are co-prime with p to the power of a. one way we can do this is using the complement. So for example, it's the total amount of numbers from 1 to p to the power of a, which is p to the power of a. And so let's just list. So we have 1, 2, ... all the way up to p, ... let's say 2p, p plus 1, right? And then we have 2p, maybe p squared, all the way to, let's say, p to the power of a, okay? So, well, the only numbers that are not co-prime with p to the power of a are what? Well, p is not co-prime with p to the power of a, right? 2p is not co-prime with p to the power of a because they all have p's, right? 3p is not co-prime with p to the power of a, all the way up to, well, p to the power of a is not co-prime with p to the power of a. Okay? But I can write p to the power of a as p to the power of a minus 1 times p. So these are the set of numbers that are not co-prime with p to the power of a. Well, how many are there? There's just 1 of them, 2 of them, 3 of them, all the way to p to the power of a minus 1 of them. So p to the power of a minus 1. So there we go. So from 1 to p to the power of a, we have p to the power of a numbers. And then we subtract the amount that are not co-prime with p to the power of a, which is p to the power of a minus 1. So this gives me the amount that are co-prime with p to the power of a. And of course, you can factor out the p to the power of a minus 1. So you get p minus 1, right? P to the power of a minus 1 times p minus 1. All right. So that's that. Okay. And you see here that if a is equal to 1, you indeed just get p minus 1. All right. So therefore, I'm just going to get rid of this. If you have n that is a positive integer, oops, this implies that phi of n is equal to phi of the product running over all primes dividing n of p to the power of v sub p of n. And phi is multiplicative, so we get that this is equal to the product of all the primes running over all the primes that divide n of phi of p to the v sub p of n. And this is just equal to the product running over all primes that divide n of p to the power of v sub p of n minus p to the power of v sub p of n minus 1. Right? Once again, we can just replace this vpn with a from here, and we get this expression. Okay. So that's it for multiplicative functions. I hope you enjoyed this video and learned something interesting and new today. Bye-bye.